Okay, good morning. Today is Thursday, November 4th. So what I'm going to do today is I'm going to continue talking about quantum mechanics from the perspective of what we call hydrogen-like atomic orbitals. So we're going to cover section 6.6. And the title of that is quantum numbers. So this is dealing with the quantum numbers. Okay. Now, the idea here is the following, just to review real briefly. We now consider the electron in an atom to be attracted to the positively charged nucleus. It's a negatively charged particle, the electron is, so it's going to be attracted to the nucleus. However, at the atomic level, and really at the subatomic level, these electrons no longer behave in ways that we might predict. So they behave more like waves. So they're standing waves that are vibrating around the nucleus, okay? And, sorry, let's close this out. And we have to apply the mathematics of waves to be able to generate information that's useful to us. We want to know certain things. So one thing we might want to know is the energy of the wave. How much energy does this wave have? Because that will allow us to do certain sets of calculations, okay? So we're going to talk about the first quantum number, which is called the principal quantum number. I mentioned this at the end of yesterday's lecture, so you can review that discussion. The symbol for it is a lowercase n, and it is the counting numbers 1, 2, 3, 4, 5, 6, 7, 8, etc., all the way up to infinity. I'm not going to go through the mathematics of how this is calculated. It's way beyond the scope of this course. It involves differential equations and integrals and matrix algebra and all that kind of stuff that you would take as a junior in mathematics. Okay. So essentially what this does then, here's the nucleus at the center. It allows us to locate the region of space that the wave is vibrating. So I'm drawing these orbitals in sort of like concentric circles, right? And they're approximately the same distance apart. That's not actually true. In fact, they're very far apart from each other. Well, actually, let me word it a little bit differently. The 90%, remember, these are 90% probabilities. Okay, so in this particular orbital, which we'll call a 1s orbital, 90% of the probability of the electron is within that little circle. Okay, obviously it's a sphere and it's a fuzzy sphere and all that kind of stuff. We'll get, ignore all those details. So the second one here is the 90% probability for the second orbital, right? And this is going to be called a 2s orbital. Okay, so the number 1, 2, 3, 4 is corresponding to these numbers here. So the one down here closest to the nucleus is the 1s orbital. The one that's further out from there is called the 2s orbital. The one that's further out from there is the 3s. So the 3s is bigger, right? As you move to higher n values, the size of the orbital increases, okay? There's a larger and larger region of space where the electron is occupied, allowed to occupy, okay? There's another aspect of this. The principal quantum number also gives us the energy. And so I'm going to try to show you, this is energy. We don't have to worry about what the units are, but I'm going to show you the relative energies of each of these orbitals, right? Remember, the orbital is the space, the geometric space the electron occupies. We'll find a little bit later that you can have 2 electrons in each orbital. Then we have the 2s. The 2s is pretty high up in energy compared to the 1s, higher in energy, right? This is increasing energy. Then the 3s is higher than 2s, but look, it's not nearly as widely spaced as the 1s to the 2s. You know, the difference in energy between 2s and 3s is much smaller than it is between 1s and 2s. And then the 4s, it's getting even closer, right? This is called convergence for those of you that talk about mathematics, right? We have certain types of series or functions that converge. This is a converging function. So it becomes 5s and then 6s. And eventually you reach infinity. And notice infinity is not that far up from like 5s or 6s. It's actually relatively close. The difference between 6s and infinity is smaller than the difference between 1s and 2s, interestingly enough, right? So what that means is if an electron is in the 1s orbital, it's a finite amount of energy to get it to infinity, which means away from the atom, just completely away from the atom. That's called ionization, okay? So it doesn't take an infinite amount of energy to remove an electron from an atom. It takes a finite amount of energy, and that's given by this function here, okay? So we draw these 90% probabilities, which we call orbitals, atomic orbitals, and they're calculated, usually they're calculated for hydrogen atom, and then we assume that other elements use essentially the same orbitals. That's not, you know, that's an assumption that may or may not be accurate, but for the most part, it works okay for our purposes. So we call them hydrogen-like atomic orbitals, the atom's orbitals, okay? So that's the principal quantum number. It gives primarily the energy, and that's something we can measure. Measuring the size of an orbital is not that easy, but we can measure energies pretty well because we can put a photon into the atom, right? Put a photon in here, measure how much energy it takes to go from 1s to 2s. It absorbs the photon or emits a photon if we make the atoms really hot, that kind of thing, right? So that's something we can measure really well. And so that's one of the reasons that this is a focus of this discussion is the energy, is because that's something we can measure, okay? Can't measure the color of an atom, can't measure the color of an electron, can't measure the smell of an atom, right? Maybe can't even measure the length of an atom or electron, but you can measure the energies. That's something we can do by using electromagnetic waves, okay? So notice I gave these names. These are names of these orbitals, 1s, 2s, 3s, and notice the pattern as you go to higher and higher s values. I'm sorry, yeah, s values. 1s, 2s, so higher and higher n values is what I should say. The energy of the orbital is higher and higher and higher. So the more likely situation, if you have an electron, is that it's going to be down here, which is referred to as the ground state. Why? Well, it's lower in energy, right? If you throw a rock into a valley, the rock is not likely to hang out, 5 feet off the ground. It's most likely to hit the ground, go down to the bottom. We call that the ground state, right? So the same is true for electrons. Their most probable position is closer to the nucleus because the nucleus is positively charged. Okay, we'll look at it. It gets kind of fun and interesting when we have multiple electrons, how they work with that. Okay, all right. Let's talk about shape now. So we've talked about energy, the principal quantum number. The second quantum number, sometimes it's called the secondary quantum number. It has different names. Most commonly, it's called the angular momentum quantum number. So this is the second one, the angular momentum quantum number. And then you think about it, okay, the symbol for this is going to be an L, but I'm going to use a lowercase script L because if you use a print L, it might look like a 1. And we don't want to use a capital because capital has a different, there is a type of angular momentum for the total angular momentum of an atom. We just wanted it of an orbital. So we're going to use lowercase L. We're all familiar with the idea of angular momentum, right? If you take a string and you tie something to the end of it, like a rock or something like that, and you spin it around, it has momentum, right? There's, you can calculate the angular momentum, MVR. So it has a velocity, it has a mass, it's moving in circular motion. So we call, we claim that it has, analogous to linear momentum, which is in a straight line. We would call this angular momentum because the angle is changing, it's going in a circle, right? So it turns out the electron also has angular momentum because it's in these orbitals. So it's as if it were in some sort of motion, circular motion. They have angular momentum. Now, the thing about this is that, if you're taking classical physics course, mechanics course, you would just, MVR, you calculate the velocity, the mass, the radius of the orbit, and you have your angular momentum. But these are waves, so we calculate them very differently. And the result of this is we get what's called the angular momentum quantum number L. And L is quantized. Much in the same way that the principal quantum number is quantized. In this case, the angular momentum, the mathematics work out that it can be 0 or 1 or 2 or 3 or 4, all the way up to the maximum possible value is n-1. And that's a key and a confusing thing for people. What that means is if your n value is, let's make up a number, 6, you cannot have an L value of 6 or greater than 6. Why? n-1 is the higher end. That's your max value. So if n equals 5, the way we interpret this, if n equals 5, L can be anything starting at 0 all the way up to n-1. It can be any of those values. So it could be 0 or 1 or 2 or 3 or 4. And then we would stop. Why? Because n-1 is 5-1, which is 4. So that would be our endpoint. So these are all possible values. They're all possible. So that's another aspect of these quantum numbers you have to become comfortable with, is that for a given value of n, you can have multiple values of L, okay? Now, the angular momentum is related to essentially what the orbital looks like. If you change the shape of an atomic orbital, its angular momentum changes. So we have several different shapes. And the first one is the case, we're familiar with that one. We called that the S, right? The S orbital, so that's the shape. And remember, this is the 90% probability. We're using that as sort of a notation to simplify things, right? It's really what, sometimes they call it a cloud. A cloud is diffuse, it takes up space, but it's not a solid object, right? All we're saying is there's a 90% probability that the electron is in that space. 100% would be an infinitely sized orbital. So that's the S, right? There's a second one, which is called the P. And these are often drawn in different ways. Sometimes they're drawn like little balloons like I'm doing right here. These are called lobes. There's a nodal plane. This one is called a P. It's called a p orbital. Those are the names of the orbitals, S, P, okay? The value of L for the S orbital is 0. The value of L for the p orbital is 1. Okay, so I'll just write it out here. L equals 0, L equals 1. Okay. So if you are given a set of quantum numbers and you see that it says L equals 1, you now know the shape of the orbital. And we use that as chemists. Chemists will use the shapes of orbitals to make predictions about chemical reactivity. If you see that the value of L is 0, then you know it's an s orbital and you know the shape. Okay. As n increases, 2, 3, 4, 5, you know it's bigger, 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 right? And higher and higher and higher energies. That's essentially the idea. The third type, the nucleus is here in the center. I kind of went over these yesterday a little bit, but I'm trying to be a little bit more thorough about it here. And it doesn't hurt to have a second introduction into something, right? There's the nucleus at the center. Yes, there are 2 nodal planes going through that particular orbital. This one has 4 lobes, right? That's all one vibration. Imagine it as a vibration. All 4 of those regions of space are vibrating at the same time. The electron occupies all 4 regions simultaneously. And again, just to remind you, this is a 2-dimensional depiction of a 3-dimensional phenomenon. This is called a d orbital. We use lowercase s, p, d. L is equal to, you probably guessed it, 2, right? L is equal to 2. And then the last one I'm going to show you has 6 lobes. And again, you'll see that I don't draw them exactly the same way each time. That's just an issue of my artistic ability. This one has 6 lobes in general. It's called an F. I won't go through the notation of where those letters come from. It turns out it's related to some of the hydrogen spectra discussion that we had earlier with the Bohr model, okay? So L equals 0, 1, 2, 3, 4. So let me make a little table that you need to memorize. So S, P, D, F. L is equal to 0, 1, 2, 3. Now, you don't need to know this part, but I'll show it for you. You can continue going on up to higher and higher ones. So 4, 5, 6, 7, 8. I don't know if L is in there actually. That's true. And you can keep going. And so physicists have tried to study these higher and higher angular momentum quantum numbers, but it's not important for us, right? Really, all of the 4 that we need to worry about are these ones right here. Okay. Those are the most important ones because they're related to the periodic table. Okay. Now, those are the first 2 quantum numbers. There's 2 more that we're going to go over, but what I want to do at this stage is I want to give you a little bit of notation here. So there's something called shell notation and subshell, shell and subshell, sorry. Okay. So here's some orbitals we can have. I'm just going to list them out. You could have a 1s orbital. N is equal to 1, L is equal to 0. You could have a 2s orbital. N is equal to 2, L is equal to 0. See how I'm going through that really quickly, right? S, P, D, F. So what I'm doing is I'm saying S, so L is equal to 0. The number in front is the N value, right? So N equals 1, L equals 0. And you could just keep drawing all kinds of atomic orbitals. And these commas, I'm just separating them so that you can see them. For P, right? I'm drawing a bunch of them. Okay, there's a bunch just to show them all, right? So I'm going to pick one randomly over here. Let's look at that one right there. N equals 4 and L is equal to 3, right? S, P, D, F, 0, 1, 2, 3. So you can figure out those first 2 quantum numbers merely by using this notation. So sometimes people call this subshell notation. I was going to call it shell notation. It's actually subshell notation, right? Subshell. And so I want to talk a little bit about this idea of shells and subshells right now. Okay. The idea, what we seem to see in terms of these atomic orbitals is that there are essentially layers of these atomic orbitals that superimpose over the same region of space. And they follow certain patterns. And so one way to imagine this is like an onion. How an onion has layers, there's physical layers in an onion, right? So the same in a sense is true for an atom. There are these layers of electric charge, layers of electrons. And the biggest kind of division of layers is called the shell. So the shell, we can think of it as all the orbitals, and I'm just saying orbital as opposed to hydrogen-like atomic orbitals to be simple. All orbitals, and I'm going to put electrons in parentheses because the electrons are in these orbitals, right? All orbitals with the same principal quantum number. Which is the same value of n. All the orbitals, all the electrons that have the same value of n are in the same shell. So you can think of that as a layer around an onion, okay? Now, if we look at this big list that I put in here, I'm going to number the shells. Let's say shell 1. All of the orbitals that I've listed here that have an n equal to 1 are just right here. That's the only one, right? Just one s, that's all there is. Okay, so what about shell 2? Let's do the second shell. Well, those are all the orbitals and all the electrons where n is equal to 2. So that would be these two right here. So it would be 2s and 2p. Shell 3. All the ones where n is equal to 3. That would be this, this, and this. Don't forget that one over there. We'll talk later about why the 4s is, I wrote that before the 3p. 3D, sorry. But in any case, 3s, 3p, 3d, shell 4. Well, that's 4. So this one, this one, this one, and then this one all the way out here, right? So 4s, 4p, 4d, and then 4f. So those are called shells. So you kind of like imagine all those orbitals are fitting around some general region of space. You know, one way might be to think of it sort of like the asteroid belt, right? So you've got the asteroid belt, which are all these little rocks circling around the sun between the orbit of Mars and Jupiter, right? So each of them are individual rocks. They're all spread out all over the place, but in general, they're in the same layer, right? They're in the same orbit around, around the sun. So it's kind of like that in a sense, okay? So that's called shell notation, if you want to call it that. The subshell notation, so subshells, and by the way, they do give names to these. Sometimes this is called the K shell, the L shell, the M shell, the N shell. You don't need to know that for this course. It's not even in your textbook, but you will see that. Sometimes in biology books, they'll put that, okay? So those are the shells. Subshells. Subshells are essentially the same two quantum numbers. Okay, so for example, these two have different L values, right? They have the same value of N, so they're in the same shell, but they have different values of L, so they're different subshells. So we would say that the 1s, this is called a subshell. It's part of the shell that has n equals 1. Now, it turns out it's the only one in there, but nonetheless, in general, the subshell is all the orbitals, all the electrons that have the same value of n and the same value of L. They have to have the same, both of them, right? So that means that the 2s is a different subshell from the 2p, right? They're not the same subshell. So a subshell is a further division of the shell, Okay, so you got a shell with all the 2s, all the 2p, and then you have subshells 2s, subshell 2p. Okay, that'll be important when we talk about Hund's rule when we get to the last couple sections here. Okay, so all of these that I wrote out here are called subshells. So this is called, the 6p subshell, right? And essentially they are divisions of the shell. So, I guess you could, I don't know, it's hard to find an analogy for that, but it's a division. So, you say shell 3, for example. You got all these orbitals, 3s, 3p, 3d. We're going to divide them up, and each of these are subshells. Okay, so you have 3 different subshells. In fact, the number of subshells for a given value of n is equal to n, right? So if n is equal to 5, you would have 5 subshells. If n is equal to 4, you have 4 subshells. So each of these are subshells. Okay, close enough. There we go. All right. So next I want to talk about the third quantum number. The third quantum number, again, this one has different names. I'm going to call it the magnetic quantum number. Okay. Now, one way to think about this, just an analogy, is that if you wanted to locate an object in space, you need 3 numbers, right? X, Y, Z, 3-dimensional space. The same is true in a sense with these quantum numbers. In order to be able to determine what you desire, or the most you can determine about an object or about these waves, is you have to have 3 numbers. So it's not X, Y, Z, it's N, L, M, and then this third one, which is called the magnetic quantum number, M sub L. So the symbol is an M for magnetic, and then lowercase l. See how the little l is down there as a subscript? That's referring to the angular momentum quantum number. Okay, it's the fact that we're really, in a sense, we are talking about angular momentum still. So here's how this plays out. M sub L, the notation is a little different than the previous 2. It can be 0. It's possible for M sub L to be 0. It can also be positive or negative. So with waves, you can get negative numbers. And see, so I'm putting plus or minus, so it could be positive 2 or positive 3 or negative 2 or negative 3. And there's, just like there was with L, there's a limit. The highest it can go is L. Not L minus 1, but L. And the lowest it can go is negative L. Okay, so here's an example. Suppose n equals 3. Well, that tells us that L could be 0 or 1 or 2. There's 3 possible values for L. So what about M sub L? Well, M sub L cannot be greater than L or less than L. It can only be as much, it can be less than, it could be like, if L is 3, M sub L could be 2 or 1, but it can't be greater than 3. And it can't be more negative than negative 3. Okay, so if L is equal to 0, that's the first case, then M sub L is limited by 0, right? That's, L is 0, so that means M sub L can't go beyond that. So it would have to be 0. So that would be M sub L, right? Only one possibility if L is equal to 0. But if L is equal to 1, here's what happens. You end up splitting it and you get 3 possible values. So what happens is if L is equal to 1, then M sub L could be 0 plus or minus 1. Well, plus or minus 1 is plus or minus L, so we would stop right there. So there you got 3 possibilities right there. So it could be minus 1 or 0 or plus 1. Now you got 3 possibilities. Well, what about 2? 2 is even more possibilities. You get 5. Why? Because you're going to go from minus L. This is how you do it. You go minus L, so minus 2, and just count up all the way to plus L, right? So minus 2 all the way to plus 2. So now you got 5 possibilities. So what happens if L is equal to 3 which would be an f orbital, right? Well, now you're going to go from -3 1, 2, 3, 4, 5. I feel like I screwed up. No, one more. +3, sorry. So -3 all the way up to +3. So you got 7 possibilities. Here you got 5. Here you got 3. Here you only got 1. Isn't that interesting? So here's how it plays out. Okay. These number of possibilities are related to what L is, right? They're related to what L is. L being 0 means you can only have one possible value of M sub L. L being 3, now you have 7 possibilities. But what does L refer to? Let's go back. L, 0, 1, 2, 3, is referring to S, P, D, F, right? So what that tells us is that if we have an s orbital, so for example, a 3s, that's a subshell, right? 3s notation, n equals 3, L equals 0. That subshell only has one value of M sub L. So it would be 3, 0, 0. And sometimes we put these in parentheses. So look at that notation there. 3 numbers separated by commas with parentheses around them. That is a way of representing all 3 of these quantum numbers. N, L, M sub L. Okay. Let's take a look at the P. I'm just going to make up a number, 4P. Okay, that's a subshell notation. So n equals 4, right? It's a p orbital, so L equals 1. Let's put a 0 there, right? But it's a 1, right? Because SPDF, 0, 1, 2, 3. Now, here's the issue. It's a p. So what do we do here? Well, if L equals 1, M sub L has 3 possibilities. So this one's actually going to have 3 possibilities. Right? And how do we interpret that physically? We interpret it that there's 3 orbitals in that subshell. So we would say that for the P subshells, there are 3 orbitals. Now, what does M sub L tell you? It says something about the behavior of the atom in a magnetic field, but more to the point, what it does is it tells you essentially the direction that the orbital is pointing. Okay, so it has to do with directionality of the orbital. So here's what happens for the p orbitals. Since we're talking about 3-dimensional space, so let's do it this way. Let's do x there, y there, and z there. Okay. Essentially what you can get is you can get an orbital that looks something like this. Okay. So there's a p orbital, right? Remember the p has 2 lobes, so there's 1. But I could also rotate it. Okay, so I could rotate it so that it's essentially centered about the XZ. There we go, right there. So I just rotated it, right? I just took it and rotated it 90 degrees. But then I could do it a third way. Okay. So now we could do it about the z-axis, rotate it about the z-axis. Okay, so see how you get 3 different what we're called orientations or directions? And from the perspective of the electron being a wave, all three are possible. It's just if that, this is an interesting aspect about waves. Waves are vibrations, right? And if you put energy into these vibrations, they start vibrating in different ways. So what happens is if the electron has enough energy, it can vibrate with this shape, which we call a p orbital, but in different directions. Okay, so there's three what we call degenerate directions, meaning they're all the same energy. Okay, so that's the idea. You could go -1, 0, or +1, so you have three possible orbitals. And then, you know, as you go up, what's going on? When you go to L = 2, you have 5 possibilities. There's just 5 different orientations. And when you get to an F orbital, there's 7 orientations. Okay, so what I'm going to do, just to kind of help you think about this, if you're talking about the S orbital, there's 1 orientation. And if you want to use the word direction. If you're talking about the P, there's 3 orientations or directions. If you're talking about the D, there's 5. And if you're talking about the F, there's 7. So it just goes up by 2 each time. And then we don't have to worry. G would be 9, right? If we were going to do G, it would be 9. It just goes up by 2 each time. The reason it's going up by 2 is because of M sub L. 0, -1, 0, +1. See, you get an extra 2 because you're starting to add numbers negative and positive. You add 1 on the negative end and 1 on the positive end each time that L goes up. Right, so you know, -2, -1, 0, +1, +2, so there's your 5. And here you would go -4 all the way up to +4, and -3 all the way up to +3. Okay, so that's why you get 7 and 9 there. Okay, now for us, that's important because this is numbers of orbitals. We're now saying there's multiple orbitals within a subshell. There can be. For the S, there's only 1 orbital, right? So what I want to do is I want to show you a notation here for these orbitals. They're diagrams. So here's one way to do this. You draw a little box and you label it. Sometimes it's labeled to the right, sometimes it's labeled underneath. I'll just put it under here. So that box, we're going to talk about why we need that box a little, you know, probably on Tuesday. Well, maybe today, maybe we'll have time. That box represents the orbital, right? That's a 1s orbital. Okay, so we're no longer drawing, you know, the fuzzy or even the 90% probability. We're just saying, hey, there's this orbital, whatever its shape is, it has a certain amount of energy. This is it. We're going to represent it with a box. And then higher in energy than the 1s orbital is the 2s orbital. And so we're going to call that the 2s orbital. Okay. Now, something funky happens when you get to the P's is in a hydrogen atom, the energy of the P orbitals is the same as the energy of the S orbitals. So the only thing that determines energy of an orbital in the hydrogen atom is the value of N. But when you look at all the other elements, it turns out that's not true. And there is a pattern where as L goes up, so if you go from S to P to D to F, the energy increases. So I'm going to show the P orbital like this. But for the P, there's actually 3, and I apologize for not drawing the orbitals the same, the boxes the same identity. It's just my artistic limitations. See how I drew 3 of them? I drew 3 because the P orbitals have 3 orientations for any given subshell, right? So this is the 2p subshell, right? This is the 2s subshell. These are both in the same shell. Shell = 2, right? This is the 1s subshell. This is the n = 1 shell, or shell 1, if you want to call it that. Okay? These are called orbital diagrams. Okay. Orbital diagrams. And they can be written vertically or they can be written horizontally. If they're written horizontally, energy increases to the right. If they're written vertically, energy increases upward, okay, vertically. So then you get the 3s. Now, I'm not telling you why the order is like this. This is the 3s, but that's also a subshell, right? Each of these is a subshell. Then you get the 3p. But then once you get up to n equals 3, L can be 0, 1, or 2. 2 is a d orbital. How many do the Ds have? 5. That subshell has 5 orbitals. 1, 2, 3, 4, 5. 3D subshell. And all of those together are shell 3. Right? N equals 3. Those are all the subshells and all the orbitals and any electrons that are in those orbitals. That's all the third shell. And you can keep going on and on and on. So notice as you get higher and higher energies, more and more different types of vibrations can take place. You can get more and more of these orbitals. When we do the electron configurations, which we're getting closer to, we're almost ready to start working on that, we'll see that that's important in terms of the structure and the electronic structure of our atoms, okay? We could keep going. The next thing would be, we've done 3D. The next thing we could is do the fourth shell, right? So the fourth shell would be n equals 4. So L would be 0, 1, 2, 3, S, P, D, F. S would have 1 orbital, P would have 3 orbitals, D would have 5 orbitals, and the F, once you get to 4F, right here, you get a lot of them, right? 7 orbitals, 7 different types of vibrations in different orientations. So there's your 4F subshell. Okay. All right, so that's a lot. It's a lot of background there, right? But this is very different kind of stuff than you've probably ever seen. You have to really do a lot of mathematics to see these sort of notation or anything like that. It really comes out of the wave mechanics, quantum chemistry. So now I'm going to show in the remaining time today, just do a couple of these ALEKS problems to give you some background on those. So let me stop share there. Let's come over here. Okay. Complete the table below. This is deducing N and L from a subshell label, right? These are subshell labels, right? Complete the table below by filling in the principal quantum number N. So just giving the value of N and then the angular momentum quantum number L. Very simple, right? So here's what you do. This notation, subshell notation, they give you the value of N. So N would be 7. Here N would be 3. Here N would be 5. Here N would be 2. That's easy, right? Then you just use the notation SPDF 0, 1, 2, 3. So if it's an S, L would be 0, angular momentum quantum number 0. If it's a D, L would be 2. If it's an F, L would be 3. If it's an S, L would be 0, right? So 2, 0, 5, 3, 3, 2, 7, 0. Okay? That's pretty simple. Let's come over here. Okay, put this on share. Deducing the allowed quantum numbers of an atomic electron, right? Electrons in atoms, okay? What is the smallest possible value of the principal quantum number for an N or a D electron? So there's gonna be 2 answers here, right? So what's the smallest value of the principal? Remember, principal is N, right? For a D electron. I misread this question. What is the smallest possible value of the principal quantum number? So what's the smallest value N can be for a D electron? Ooh, okay, well, that's an interesting question. Okay, well, let's put it this way. L can be 0, 1, 2, 3, all the way up to n minus 1, right? Okay, and then we know that L is 0. This is an S. This is a P. This is a D. And this is an F. So we're talking about the case that L is equal to 2, right? Okay, well, how do we figure out the range of what L can be? Well, we do it by n minus 1, right? So if n, let's just go through some possibilities. Suppose n is equal to 2. L could be 0 or 1, right? It can never be as large as n. Well, that's an S and a P, so that doesn't work. You can't get a d orbital if n is equal to 2. And that's why there is no 2d orbital. So let's go up to the next one, n equals 3. Well, now L can be 0, 1, or 2. Well, that's SPD. Well, there you go, right there. If L is 2, that's a d orbital. When can that happen? If n is at least 3. So if n is 3, you can get a d orbital. And that's why we have 3d orbitals, but not 1d or 2d. You can have higher, you can have 4d, 5d, but the minimum value would be n equals 3. Okay, kind of cool. Calculating the capacity of electron subshells. The capacity. Now, this is interesting. We're going to have to add one more aspect of this. Here's some electron subshells. I'm going to fill this all out. Principal quantum number, angular momentum, quantum number L, just what we did with the first example. 3D, n would be 3, L would be 2, 0, 1, 2, SPD. 5s, n would be 5, L would be 0. 2s, n would be 2, L would be 0. So that's easy. But what's the maximum number of electrons in each of these subshell? Okay, so I want to show that to you because it actually involves one more important concept. So here's our subshell, 3D, 5s, 2s. N would be 3, 5, and 2. L would be 2, 0, and 0. And then the maximum number of electrons. Okay, this actually gets us into something called the Pauli exclusion principle. Wolfgang Pauli. I don't need to capitalize that. Okay, a principle is an idea, something we observe. The Pauli exclusion principle, really, I guess it should be called the Pauli exclusion law, says that in an atom, each electron must have a unique set of quantum numbers. Okay, and those quantum numbers are n, L, m sub L, and there's a fourth one, m sub s. What the Pauli exclusion principle says is no two electrons in the same atom can have all 4 of those quantum numbers be identical. Any 3 can be identical, but not all 4. At least one quantum number has to be different. Okay, so for example, if the atom has an electron, I'll call it electron 6, the 6th electron in the atom. And let's say it's, 3, 2, plus 1, comma. I haven't told you what that is. And then electron 7. 3, 2, plus 1. This number here has to be different than this one here because they can't have the same 4 numbers. It's impossible according to the Pauli exclusion principle, which appears to be a very, very fundamental aspect of our universe. Okay. So what's this 4th quantum number? It turns out the 4th quantum number is not really about the atom itself or the orbitals. It's really about the intrinsic property of an electron. It's called the magnetic spin. That's where the S comes from. Quantum number. So MS. For the electron, it has a property such that it behaves as though it were spinning. Okay? It behaves as though it were spinning. And it can spin in 2 different, if we want to call them, orientations. This is not something we can really come up with a great analogy for. It's behaving as though it were spinning one direction or the other, but it is actually not. And so I want to be careful about the words that I use. Let's be more careful and just say there are 2 possible values. It can spin with a plus 1/2 if m sub s equals plus 1/2. We call that electron spin up. I'm not going to go through the whole experiment and how this was figured out. Some of my earlier videos show that from last semester. If m sub s is equal to minus 1/2, it's spin down. Okay, spin up or spin down. It's represented with an arrow pointing upward or an arrow pointing downward. Kind of cool notation. And when we get into section 6.7 and 6.8, we'll start looking at like how we can use this notation for different things. So now here's to answer this question. Here's how this plays out. Electron 6, let's say it's plus 1/2. That means that electron 7 would have to be minus 1/2, right? They have to be different because no 2 electrons in the same atom can have all 4 numbers be the same simultaneously. So one could be 1/2 and the other could be minus 1/2. That's possible, but they cannot be both of them plus 1/2 or both of them minus 1/2. That's not possible. Now an orbital, the 3 numbers, this 3 numbers here, they tell you about the orbital. That's the actual orbital. 3, 2, plus 1, 3, 2, minus 1, 3, 2, 0, right? But here's what this is kind of cool. What it tells you is that if the first 3 numbers are the same, it's the same orbital, right? So you can think of this as an address, right? Like if I say 645 East 26, okay? Well, that's a number, that's a second number, right? Those are 2 locating values, okay? Then I could say 3rd floor. All right, now I've got 3 values. So I could write this as 645, comma, 26, comma, 3, right? But now, suppose I want to know the apartment. I need a 4th one, right? So 4, I'm sorry. So E. So I put an E there. Here's our 4th one right there, right? Now, if I say that people live in different apartments and they're not in the same apartment, then that means the second person cannot be 645, 26, 3rd floor apartment E. That's impossible. If they're in a different apartment, one of those digits has to be different. Now, here's what the way this plays out in terms of orbitals. Since this 4th digit can be different, one or the other, 2 possible values for the electron. Different particles have different set of possibilities. The photon can have different values. But for the electron, it's either plus 1/2 or minus 1/2. That means there's 2 possibilities. So you can have 2 electrons in an orbital. That's what that means. You could have in one orbital 3, 2 plus 1 plus a half. And you could have 3, 2, plus 1, minus a half. The first 3 digits tell you the orbital. So they all are the same orbital. Different values of m sub s, different electrons. Okay? If m sub s were the same, they'd be the same electron, right? In any case, there are 2 possibilities. So that means each orbital can have a maximum of 2 electrons. An orbital can be empty, 0. It can have 1 electron, 1. And now as we can say they can have up to 2. So here's how we deal with this. It's a little tricky. You have to be careful with this calculation. Maximum number of electrons in the subshell. First, you have to find the number of orbitals. So, if I were going to have you do this, I would make another column. Number of orbitals. We already went over that. If L is equal to 2, that's a d orbital. D orbital has 5 orbitals. D subshell has 5 orbitals. This is an S. S only has 1 orbital. Remember, S is 1 orbital, P is 3, D is 5, F is 7. This is an S, so only has 1 orbital. So now, maximum electrons. Well, each orbital can have a maximum of 2 electrons. So it's just 5 times 2, which is 10. 1 times 2, which is 2. 1 times 2, which is 2. So the 3D subshell can have up to 10 electrons. The 5s subshell can have up to 2. And the 2s subshell can have up to 2. Okay, there you go. Okay, the last problem has to do with, again, the notation, which says knowing the subshells of the electron shell, so subshells of a shell, fill in the missing information from this table. Okay, so let's see. So for example, if you're in shell 2, you can have 2s and 2p. Why? Because if n equals 2, L can be 0 or 1. 0, 1 is s and p, so 2s, 2p. How many orbitals? Well, the s only has 1 orbital. The p only has, or the p has 3. How many electrons could you have? Well, if you only have 1 orbital, 1 times 2 is 2. If you have 3 orbitals, 3 times 2 is 6. So you can have 2 here and 6 there. That adds up to 8 electrons, by the way, and we'll get to that 8 electron rule a little bit later. Okay. 1, shell 1. Okay, well, shell 1 can only have 1 s, right? N is equal to 1, so L can only go up to n minus 1, which would be 1 minus 1, which is 0, so L is 0, so 1s. How many electrons? The s only has 1 orbital, so 2 electrons, 1 times 2. Now you get up to 4, right? So 4, now you can have your S, P, D, F, right? 0, 1, 2, 3. So you could have 4s, 4p, 4d, and 4f. Okay. Now I want to show you, I just have a minute left here, 2 actually. I just want to show you, this is leading into what we're going to do Tuesday, which is this using those 4 quantum numbers. Remember I showed you these diagrams? I think I wrote them like this, right? No, I guess I wrote them over here. Oops. Sorry, I was canceled. Okay, there we go. So what I said was, since you've only got 1 orbital, you can have a maximum of 2 electrons, spin up, spin down, and then I said use the arrows to do spin up, arrow pointing up is spin up, arrow pointing down is spin down. So when you're putting in the maximum number of electrons, what you do is you put the spin up first. This is, you don't, I mean, there's no physical rule that says it has to be spin up, because spin up is arbitrary, what we consider spin up, okay? But by convention, by agreement, we put the first one spin up. So that is an electron spinning up. The second one we do spin down, right? And this would be the maximum number of electrons you can put in. You can put up to 2. Why? Because they're both of these electrons are 1, 0, 0. One of them is plus a half. The other one is minus a half, right? So that's why you can put up to 2 electrons. So that would be the notation using the arrows. So that's where those diagrams come into play. Same thing here. The first one you would put in spin up. The second one you'd put spin down. Then we're going to get into this next week. This has 3 orbitals, so it has up to 6 electrons. So notice how I'm filling this out. I'm going across first. That's a phenomenon called Hund's rule. So you do 1 spin up, 1 spin up, 1 spin up in each of the orbitals, and then spin down, and spin down. So you can get up to 6 electrons max, right? Here you can have 2 electrons max, and here you can have 2 electrons max. So that kind of gets you into the last couple of topics of this chapter. So I will work on those, I guess, on Tuesday. We may wrap it up on Tuesday. We'll see. We'll see how long it takes me, but certainly by Wednesday, we'll be done with that. And then that leads us into chapter 8, which is chemical bonding. So at least by the end of next week, maybe even the middle of next week, we should be working on chemical bonding chapter 8. Okay. Have a great day.